Well, hello, I'm Monica Beckwith. I'm a JVM performance engineer, and thank you for Riga Dev Days for having me here. This is my first time presenting and first time in Riga, so I was very excited for the trip, except for the jet lag part of it, which usually happens right about now because it's about 5 a.m. my time, so I'm crashing slightly. But I hope to talk more about performance engineering and the hotspot virtual machine and trying to tie them together as to what optimizations have gone into the execution engine for OpenJDK Hotspot or even Oracle's Hotspot, which are similar. So, like I said, I'm a JVM performance engineer. I worked with Oracle and prior to that Sun Microsystems, and before that I was a compiler engineer and moved to JVM JIT compilation engineering at Advanced Micro Devices. So I've done performance for more than a decade, and basically most of it has been on Hotspot virtual machine. I worked with the JVM heuristics. I worked with garbage collection, like the algorithm, as well as optimization of allocations, and then JIT compilation itself, like the generated code, optimizing the generated code on different architectures like x86, Spark. So that's about me. What I'm going to do today, like I said, I'm going to talk about performance engineering, the trifecta of performance, and the Hotspot virtual machine. So the helpers in the Hotspot virtual machine are what I call the execution engine and the runtime. So I'll talk about how performance impacts innovation in optimizations in the execution engine and runtime. The slide deck that I have is going to go over an hour, but what I'm going to do is kind of give the overview, and we may not be able to talk about certain optimization like compressed loops, which come later on in my slide, but the deck is complete, and you guys will have the deck to go over the slides later. And then eventually I would like I said, talk about the various optimizations. So without wasting any time, I want to dive into the Hotspot virtual machine. So we have your Java application, and that runs on the Java VM with the help of Java API, right? This could run on a virtualized environment in the cloud, wherever, but eventually it has to work on a hardware. And that's because that's where the JIT optimizations kick in, trying to optimize on the hardware that you're running on. Okay, most of us know about the Java runtime environment. That's what we download off Oracle's website or from OpenJDK, right? So the JRE, which is the Java runtime environment, comprises of the Java API and the Java virtual machine. So the helpers that I'm going to talk about today, like I said, are the runtime and the execution engine. So let's quickly look at the execution engine. So we have the heap management, which is we call as garbage collection. And then we have the compilation, JIT compilation, and ahead of time that's in Java 9. So what is garbage collection? So many people know garbage collection as reclamation. You're trying to get your space back, trying to reclaim memory. But garbage collection, because it's memory management, it also involves allocation. So when you're thinking about garbage collection, don't just think about getting your space back, but think about optimizing allocations as well. And we'll talk about that shortly. What about compilation? So we all know static compilers, right? Like your favorite C compiler. But there is also ahead of time compilation. So when we talk about dynamic compilation, we're talking mostly about like JIT compilation in this particular case, which means just-in-time compilation. So it happens just in time when you need it. But ahead-of-time compilation can be very useful for shared code. So you can optimize and have this compiled code ready for use when you need it. So it kind of helps with startup time. So you don't have to do just in time if you already know that you can optimize libraries as well ahead of time. And the next two are what Hotspot has been using for a long time. And they're called the profile-guided optimizations and adaptive optimizations. And in my talk, I'll talk more about those shortly. So what about runtime? So we all know as the runtime as the interpreter, right? So at startup, you have, it starts in the interpreter mode, Hotspot virtual machine. But runtime also does VM class loading and a bunch of other things shown here. So we have the bytecode verification and synchronization, thread management. If you're more interested in the runtime, there's a link right there. It's available in the slide deck. You can read more about the runtime at that link. So as performance engineers, what we're interested in is the runtime goal, which is simple, converting bytecode into native code, right? So, and to achieve, how do we achieve that goal? How do we optimize getting from bytecode to native code is what performance engineers always strive to do. So now that we know, we have an overview of the Hotspot virtual machine, let's talk about performance and how we can tie them together. So if somebody asked me what drives innovation and performance, I would talk about the trifecta of performance. So basically it's responsiveness, it's footprint, and then throughput, okay? So what do I mean by responsiveness? If I send a stimulus, you know, how much time, how soon do I get the response? So basically if I want to write to my database, for example, so I send my write command, and how soon does it update, whatever, right? So that's, in simple terms, is responsiveness. What about footprint? Footprint is the size of your application, data, everything on the system, the actual in-memory size of your application and data and everything. So as a performance engineer, I would want to optimize this. So the way I would optimize is maybe remove the redundancies and maybe compact, right? So how much more can I fit in? That's the goal always, is how much more can I fit in the space? And then the third one is throughput. How can I maximize operations per second? You know, I want to make sure that I am doing as many operations, like I'm utilizing all my cores and everything and trying to get in more operations per second. So that's the throughput goal, right? So now how do all three, the trifecta, how do they fit in with the Hotspot's execution engine? So let's start with responsiveness. So I'm going to talk about responsiveness with respect to the execution engine and the runtime, with respect to the Hotspot virtual machine. So in the execution engine, like I said, is garbage collection and compilation. So what about responsiveness and GC, garbage collection? So to improve responsiveness in memory management in Hotspot, we have faster allocation paths. We have something known as thread local allocation buffers, and I'll talk more about them briefly. So there's optimizations to improve allocations. There's also optimization to improve reclamation. So, and then we'll talk more about that. So I'm going to only cover three of the garbage collectors. There are more garbage collectors in Hotspot virtual machine. So I'm going to cover the throughput garbage collector, which is also called the parallel garbage collector. I'm going to talk about the mostly concurrent mark and sweep, which is also known as CMS, and then G1GC, which is garbage first garbage collector. We'll talk about how the reclamation is handled differently in all three of them. And then the other way to improve responsiveness is to do more work concurrently. So most of the garbage collectors in OpenJDK Hotspot or this Oracle Hotspot virtual machine, they have stop the world pauses. So what that means is that all your application threads will come to a halt, and the garbage collectors will do their work, either compacting or whatever, or marking. And but to be able to to improve responsiveness, some of the work can be shifted to be done more concurrently. What that means is your application's threads can still work, and your garbage collection threads are working concurrently with your application threads. We'll talk more about the algorithms, how they handle that. Next is responsiveness and compilation. Okay. So I already mentioned about the startup time improvement that ahead-of-time compilation brings about. And then we have something called the adaptive optimizer. So most of your static compilation techniques, like vectorization and intrinsics, are also available in OpenJDK Hotspot virtual machine. But OpenJDK Hotspot also has something that is advanced inlining optimizations and other such optimizations, which I'll cover if time permits. And then, of course, locking improvements. Now, locking improvements, I put it here, and then I'll talk about it in runtime as well, because it kind of straddles both the spaces. It's compilation as well as runtime improvements. So like I mentioned, in runtime also, I'm talking about locking improvements. And the next one is class data sharing. So if you have not looked at class data sharing, it's only available with a couple of GCs. And what it does is, if you have code that's shareable, and it helps reduce with the startup time, similar to what I had mentioned with ahead-of-time compilation. So now we spoke about responsiveness, and then let's move on to footprint. So again, how do we reduce the size, right? So with respect to GC, of course, we have compaction, right? So what is compaction? So if you let your garbage collector run over, so basically you're allocating, you're promoting with the most of the garbage collectors in OpenJDK Hotspot, you have something called multi-generation. Basically, you have a young generation and an old generation, and as you age objects, they get promoted into the old generation. So over time, your old generation, if you don't do compaction, could look like a bunch of live objects, dead objects, live objects dead. So it could look like Swiss cheese. So some of the GC algorithms achieve compaction. What that means is kind of clubbing your live objects together at the lower end of the heap. Some garbage collectors in OpenJDK Hotspot do partial compaction as well, which is also known as incremental compaction. And in G1 GC terms, it's called mixed garbage collection. There are algorithm refinements in reducing allocations. So if you reduce allocations, you're kind of helping with footprint reduction as well. And the way we do it in OpenJDK Hotspot is either allocating depth first or breadth first, or other like escape analysis and stuff like that. And then we have compressed headers. So compressed headers is something that came with compressed object pointers, ordinary object pointers. And I'll talk about compressed headers if we get some time. What about footprint and compilation? So inlining, first of all, is the most important optimization that OpenJDK Hotspot brings about. We have escape analysis that I spoke about, which looks if an allocation can escape from the method. And then we have something called de-optimization. Because Java has dynamic loading of classes, and so there's many times some things that were presumed to be hot more when it's profiled, it may not be true anymore. So then we need to be able to de-optimize that particular code that we thought was hot. So that is that can be done in Java, and that is called zombie code or de-optimized code. What about footprint and the runtime? I spoke about compressed OOPs and compressed class pointers. We have something called code caches, which stores your compiled native code, and then we have class data sharing. So let's talk about throughput and the execution engine now. So we covered responsiveness, we covered footprint, and now the optimizations that have gone into OpenJDK Hotspot to improve throughput. So looking at garbage collection, we have multi-threaded work stealing. So, and one of the examples would be the Perl GC. Actually, all garbage collections have multi-threaded work stealing, but the first time it was introduced in the old generation was with Perl GC. What that means is when your application threads are paused and your garbage collection threads are doing the work, you can employ multiple garbage collection threads, and you can have work queues, and they can perform something called work stealing. And there's a protocol called termination protocol. So this is highly advanced, and it's basically all your queuing theories and stuff like that are implemented. So that helps with throughput, trying to get the work done quicker. Then we have multi-generation again. I briefly covered it earlier. So most of the garbage collectors in OpenJDK Hotspot have young generation and an old generation, and I will talk more about that. So that helps with throughput because now you can age objects and only promote when necessary. Multi-phase marking again, so you can divide. So marking doesn't need to be a long stop the world pause. You can do it, some of the work concurrently, some of the work can be done in different stages. So that helps with throughput as well. And I mentioned about compaction, either full compaction or incremental compaction. So what about throughput and compilation? So we have the JIT compiler, of course, right? So the just-in-time compilation helps with throughput. And then we have intrinsics. Basically, these are hand-optimized code that help with throughput, because now you're going to an optimized level of code instead of just using a generic optimization. Vectorization, again, for SIMD instructions, multiple data, single input, multiple data. These are with x86, there's a lot of SIMD instructions. So a hotspot can use vectorization. It's not very advanced, it's in infancy. So if you're used to static compilers and you're used to vectorization, don't expect the same out of hotspot, because again, it's a dynamic compilation. And think about how intrinsics with static compilers are kind of much easier, right? So with dynamic compilation, vectorization doesn't. I may be covering and talking briefly about what Hotspot does right now, but I'll also include a link to the paper that the optimizations are based on. Okay, and then loop unrolling, of course. What about runtime and throughput? Of course, we have compressed OOPs. We already covered that, and then compressed class pointers. So that both of them help throughput. So now let's dive into these optimizations, okay? The first I want to cover are the garbage collection facts, and then the innovations based on the throughput and responsiveness and footprint. So, so the way the garbage collection evolved in Hotspot was because of throughput and latency pressures, right? So they're the two main drivers, and footprint kind of took a back seat. So throughput and latency are the two main drivers for refinement of GC algorithms. Almost all GCs in OpenJDK Hotspot are generational. We have Shenandoah, which is not generational. And then, all right, so if I put all those things that we discussed earlier and we had clubbed them individually, if I put them all together, so we have the responsiveness column there, then we have the throughput column, and then we have the footprint column, okay? Another way to look at that would be, so another way to look at that would be if I could explain each of them and kind of put them together with respect to the GC algorithms, and that's what I'm going to do now. So let's first look at the multi-generational heap, right? So like I mentioned, we have the young generation and we have the old generation. So the young generation further has the Eden space and the survivor spaces. So here I've shown the same thing again. So, but here now I can talk more about how allocations happen. So, okay. Okay, so allocations, most allocations happen in Eden space, okay? And then after you age the object, so when a collection happens, most of the live objects will be moved, or all the live objects actually, will be moved to the survivor zero space, which is also known as 2 space, and the other one is called the from space. So at any given time, S0 and S1 will be either 2 or from. So, so as the objects are surviving, and they're also aged, so there's an age counter, which tells the age of these survivors. And once you cross the age threshold, those objects can be promoted, which is also known as tenured. Okay? By promotion means they'll get moved to the old generation. And then old generation collection kicks in. So if I, again, like I said, if I put all those optimizations into this particular format, so the faster allocation paths belong to the allocation area of the memory management. Multiple threaded work stealing belongs to the reclamation path. Faster reclamation also belongs to the reclamation. And now the reason I'm going to say allocations and promotions together, because some of the optimizations like TLABs also apply to PLABs, like promotion local access buffers, right? So that's why, it's not fair just to say allocations, but also for promotions, those techniques help. So you have multiple generation, which helps with the promotions as well as reclamation, and more work done concurrently, multi-phased marking, incremental compaction. So those things are basically different areas of optimizations within memory management. So let's talk about allocations quickly. So like I mentioned, multi-generation heap as well as faster allocation paths belong to allocation group. And then, and we also spoke about how most allocations happen in the Eden space. So, okay. So, and we also spoke about TLABs. So here are different ways that people refer to TLABs. They call it lock-free allocation. They also call it fast path allocation. There's also the slow path allocation. So, so these are different terminologies. So if I had to explain TLABs in a very simplified manner, each allocating thread has a TLAB. So, and then the Eden space is divided into this TLAB areas for each thread. They're not, at the very beginning, they're similar sized, but they get resized based on your allocation, the thread's allocation pattern. So for example, if I had 5 threads, you'll see 5 different TLABs. Okay, and as your allocations happen, your Eden gets full, and then at the first collection, the young collection, you will see that your survivor space gets filled with surviving objects. Eventually, they get promoted after aging, like I mentioned. So once your old generation is full, then we have old generation collection. And these collections are also called reclamation. So there are different terminologies, but they kind of mean the same thing, because you're reclaiming the heap. For reclamation, as I mentioned, there are lots of optimizations, such as the multi-phase marking, but the algorithms also differ, okay, especially for old generation collection. So we talked about Eden, survivors, young generation, old generation. So let's talk about the algorithms. So all generational OpenGDK hotspot garbage collectors have similar algorithm for young collection. So it's the same, it employs multiple threads, it stopped the world, and it's the same for all three that I'm going to cover today. But the old generation has different garbage collection algorithms. Okay? So we'll concentrate more on that, and that's what determines if it's a parallel collector or a CMS or a G1GC. It's not the young generation collection, it's how the old generation is reclaimed or collected. So for parallel GC, which is also known as the throughput collector, I call it the throughput maximizer, these are the optimizations that went in. So when I talked about innovations in garbage collection, and I talked about multiple threads, multi-generation, compacting collector, and faster reclamation via P-labs and T-labs. So those are the things that help throughput GC, called parallel GC, achieve better throughput. So it doesn't, what you don't see here is anything done concurrently. So there's no concurrent work. It's all stop the world. The next is latency sensitive GC, is what I like to call it, but people know it as CMS, which is mostly concurrent mark and sweep. And what are the optimizations that went into CMS? The multiple generations, of course, because we have the young generation and the old generation, and then the multi-threaded workers. Okay, but not the most effective are the next two, which there's one that you don't see, and that's the most effective one. So more work is done concurrently. That's why it's called mostly concurrent mark and sweep. And then the multi-phased markings, like I said, that's what the work is done concurrently. What you don't see here is compaction, and that's the most effective, and that's why it's latency sensitive garbage collection. So CMS doesn't do compaction. What happens with CMS is the old generation does in-space deallocation for objects that are not live. Eventually, over time, it will lead to fragmentation, and then there's a fallback garbage collector, which is similar to what you may have seen with serial GC, which is a single-threaded compacting collector. So, so that's how CMS achieves its latency sensitivity, is by not doing compaction at all, just quick in-space deallocation. Okay. So G1GC is somewhere in the middle. What G1GC does is everything that's on the left. It does multi-generation heap, it has multi-thread workers, more work done concurrently, multi-phased marking, also has incremental compacting. So it doesn't have the drawback of CMS where eventually you'll have fragmented heap or concurrent mode failures. G1GC doesn't have that. And the way it combats the full stop the world pause of old generation collection in parallel GC is by pausing incrementally. So you have multiple thresholds in G1GC where you could say that I only want my heap to be filled up to, like, say 95% or whatever. So, and then there's like the marking threshold where you say as soon as my heap crosses 45% occupancy, start the marking cycle. So there are multiple thresholds which help you determine how soon you want the incremental collection to start happening and how many incremental collections do you want, And what makes these incremental collections more helpful is having a pause time goal. So G1 does have a prediction logic where you can give a hint saying that I would like my pause time to be 200 milliseconds. It's not a hard stop, so it'll try to achieve 200 milliseconds, and that kind of, with the help of prediction logic, over time you will see that if garbage collection is tuned well, then your application will try to behave as the way you desire it. So it'll try to achieve your pause time goals over time. So those are the three hotspot GCs that I was going to cover. Then we'll move on to compilation engines and the optimizations in the compilation engine. So like I mentioned, adaptive optimization and profile-guided optimizations are the two optimizations in the for hotspot virtual machine. And again, putting all the three tables together, we have all the optimizations or major optimizations that are in the hotspot compilation engine. We may be able to cover, we'll definitely cover all of them, so I'm just going to say these are the ones that we're going to cover mostly within the time that we have, which is only 13 minutes. Wow. Okay. So how does hotspot achieve JIT compilation? So there are counters. Okay, hotspot starts in interpreter mode, and there are counters that count loop backs, so loops basically, and then you have method entries. So every time you have the same method is invoked again and again, the counter increments, and then same goes on as the loop. So once these thresholds are crossed, so there's something called compile threshold. So once the threshold is crossed, then that particular method, which is supposedly hot method, is compiled. That's called just-in-time compilation with profile-guided compilation. You could also have on-stack replacement. So for those hot loops, like I mentioned, you could choose to just optimize those loops, and you can replace them on stack. So that's why it's called on-stack replacement. So OSR is what is the compilation lingo. So prior to tiered compilation, hotspot used to have C1 and C2, also known as client and server compilers. So the difference was that this client compiler was very helpful in decreasing your startup time, because it did very few optimizations, right? So it was working. It starts an interpreter, and the compilation threshold was very low as well. So you start compiling with client compiler, but there are not that many optimizations. With C2, also known as server compiler, it's the same way. You start in the interpreter, but the compilation threshold is very high. So if your application has a bunch of hot methods and they cross that threshold, then that's the only time they would be compiled. So, and then C2 includes a lot of high performance optimizations. So I think with JDK 8, we had tiered compilation, which kind of, well, I think it may have been in JDK 7 too, but it wasn't enabled by default until JDK 8. So, of course, so it helped improve startup as well as your long-running server application compilations as well. So tiered compilation has 5 different levels of compilation. So it starts in interpreter, and then there are 3 levels of compilation at C1, which is the client compiler level. So first, the C1 will have no profiling, and then the second level of C1 would have the loopback counters and the method entry counters. And the third one is like full, C1 with full profiling. And eventually it goes to C2. So the last level is C2. So those are the levels in tiered compilation. One thing to note with respect to, because I was talking about code cache earlier, how it helps with the footprint and everything. But one thing to note, with the introduction of tiered compilation, it has some effects on code cache. So basically, the code cache gets bigger or needs more space. Like I mentioned, code cache is where your compiled native code resides. So when I talk about compilation threshold, is right after that point, things will start getting compiled. Now with tiered compilation, the first level of compilation threshold is only 100 invocations. So if your method has 100 invocations, it'll get compiled. So imagine how much of a bloat that does on your code cache. And then when the performance engineering team was studying the effects, we found out that code cache needs to be 5x larger, 5 times larger than what it used to be for non-tiered. So now, with JDK8, the default changed from 48 megabytes to 240 megabytes. So if you need more, then you can use something called reserved code cache size. You can change your code cache size based on using that particular option. So now let's talk about the advanced optimizations, also known as adaptive optimization. So you start up in Interpreter, and then you have profiling of hotspots, critical hotspots, trying to figure out which ones to compile or not. And then you have you start doing JIT optimizations. But there's something called de-optimization. Okay, and then you could eventually, because of de-optimization, you can probably go back into interpreter mode. Okay, so let's talk about that. So basically, de-optimizations are your oopsies. Like you did something, and then you want to take a step back and say, I didn't quite want to do that. And Hotspot does that. So you could have dependencies in validation. You could have class unloading, like I said, because of the dynamic class loading. And then you may have taken some uncommon. You thought that this method was hot, but all of a sudden it's not quite hot. So you optimized it, but that path was only taken for, say, 100 invocations or whatever, right? So also your profiling information could be wrong, because like I said, you took an uncommon path and then you got the wrong information. Usually I have an example because Hotspot does provide options on how to look at your print compilation details. So you can look at that and it'll tell you that your code has been zombied or the code has been de-optimized from a level from level 2. So when you're changing the levels of tiered compilation, you're going from 2 to 4, for example, the code that was at level 2 has to be de-optimized and then collected so the code cache pressure can be relieved. So I don't have that now because I don't have much time. So moving on to escape analysis. Like I mentioned, it's very simple. It's trying to find out if your allocations can escape. So how do we do that? So we're going to make sure it's not stored to a static field or non-static field of an external object. It's not returned from the method, of course, and not passed as a parameter to another method where it can escape. So if I had to put it together as, so basically, if it's allocated, if the allocated object does not escape the compiled method and allocated object not passed as a parameter, then you can remove allocation and keep the field values in registers. And if the allocated object doesn't escape the compiled method, but allocated object is passed as a parameter, then you can still remove some locks associated with the object and use optimized compare instructions. That's what the JIT does internally. Okay? How about runtime innovations? So I have 5 minutes. I'll start with it. We may not be able to finish it, but we'll start with this one. So again, putting all the tables together, we have, so we'll talk about compressed tubes and compressed class pointers. And we already covered code cache, so we won't talk about that. So we have a Java object, and all of us know the Java object has header and body, right? And a couple of things to know before we talk about compressed tube optimizations. Objects are always 8-byte aligned, and that's the reason why we can do optimizations like compressed tubes. Fields are aligned by the type. Fields can fill a gap that may be required for alignment purposes, and are accessed using offsets. All fields are accessed using offsets from the start of the object. Okay, so this is important just because when I show you the layout, the object layout, you need to know how fields are accessed. And anyway, so this is an important bit of information here. So I used a tool called Java Object Layout, JOL. It's to analyze Java Object Layout, of course. And this is the instruction that, so I wanted to see the internals, basically field layout and contents and object header. And I wanted to show what compressed OOPS and compressed headers, how it is achieved within the object. So let's first look at compressed class pointers with 3-bit shift. And basically 3-bit shift is where, when I talked about object alignment, 8-byte align, that's the 3-bit shift, okay? So what does a Java header, object header have? So it has the mark word, and then we have the class pointer, right? So it's the size of your native pointer. So if you are on a 64-bit system, so the class would be your 64-bit, like the pointer would be 64-bit. So, and then if it's an array object, then you have array length as well as a part of the header. So if I wanted to look at the uncompressed object layout, it would look something like that. So I looked at 8-byte array, and what you see here are the first 2 lines with size of total of 8 bytes is your mark word. Okay, and then the next 2. So if you see, you can see the object headers. The first 5 are object headers. So the next 2 are your class pointer. Okay, and then the next one you see is your object header right there as well, and that's your array length because it's an 8-byte array. All right, so you see the array length as in the next 4 bytes. And then you have something called alignment padding. Remember I mentioned that sometimes you need to maintain alignment, you can do padding. So that's what is done here. That's 4 bytes. And then of course the next one is your byte array. So when we see the same thing with compressed OOPS turned on, what you can see is the mark word is the same. And then you have the next one is only 4 bytes. And remember, it was 8 bytes earlier. And that's your compressed class pointer. So that's how you can visualize. So that's what happens. So basically, instead of 8 bytes, now we just need 4 bytes. And that's the compressed class pointer optimization. And then, of course, everything else is similar. This is your array length, and then the next is 8 byte. What you see also missing here is the alignment. Remember, in the uncompressed stage, we had the alignment issue, so we had to have some padding. Here, you don't see any padding. So if I compare them side by side, what you see is that the compressed one needed 24 bytes, and the uncompressed one needed 32 bytes. So, of course, 4 byte was because of the alignment, but also the other ones was because of the compressed class pointer, right? So we save about 8 bytes. Okay, so going back to the optimizations, what about compressed OOPS? Like, how do you visualize compressed OOPS optimization? So for that, I'm going to still use Java Object Layout, and I'm going to look at class. So JOL of a class. So you can see that you see the offset on the left. It's the same thing. Offset on the left, and then the size, the type, the description, and the value. So in this particular case, it's 168 bytes, the instance, okay? So the first one is the object header, which is 16 bytes. And if you go dive deep into that, you'll see the offsets again and the size. So, just looking at the size for now, when you look at the same thing with compressed, enabled, you see the size has changed. Now the object header is only 12 bytes instead of 16. It's only 12 bytes, and the size of all those the class.module, class.name, all those have changed to 4. So basically, that's what compressed OOPS enables. It enables you to go from 8 bytes down to 4 bytes because that's all you need. So it's by achieving the 3-bit shift. So you're not using the 64-bit pointers, you're using only 32-bit pointers, okay? So we achieved compressed class as well as compressed OOPS shift. So I was talking about the 3-bit shift all the time, right? So if you look at the optimization, this is what you will see. So the wide ordinary object pointer, which is your regular 64-bit pointer, can be changed into a narrow OOP, which is your 32-bit pointer, by shifting, by 3-bit shifting. And then, of course, since all fields can be accessed by the offset, then you have something called the field offset, okay? So if I put it in a tabular form again, so if your heap size, and within compressed OOPS, there are various optimizations that can be done called zero-based OOPS and stuff like that. So if your heap size is already less than 4 gigs, you don't need any encoding or decoding because your wide OOP is your narrow OOP because it's 4 gig is basically addressable by 32 bits, right? So now if it's it's more than 4 gigs, but it's less than 28 gigs, you can do something called zero-based. So all you need is your narrow OOP can be shifted by 3, okay? Then between 28 and 32, you have your regular optimization, which is what I had shown earlier. And then with, I think, JDK 8, you can also go a step further and change your alignment. Remember, by default, the objects are aligned on 8-byte boundaries, right? So if you change the alignment, then you could achieve even more addressable space. And in this case, if you see, the shifting has changed from 3 bits to 4 bits because we changed the alignment. So kind of putting it all together again, you see if it's less than 4, you don't need any shifting. If it's between 4 and 28, you shift by 3. Even if it's less than 32, you shift by 3. But if you want to go to less than 64, if you think that compressed OOPS are going to benefit you, then you change the alignment and to 16 bytes, and then you change the shift by. Actually, it automatically will do that for you. So JDK 8 does all this automatically. And that's pretty much it, I think. I went really fast, I know, and I'm sorry, but I had a lot of optimizations to cover, and I'm open to questions, if you have questions. Okay, yes.
How does adaptive sizing work? How does adaptive sizing work?
Adaptive sizing?
Yeah.
In
the throughput collector.
Good question. So I think it's disabled now. Okay. So this is very interesting because when prior to adaptive sizing, what used to happen is that we could only grow the young generation up to X. And then because right after that, we had the old generation that needed to start. So the young generation could never go beyond certain point. But now, with the introduction of adaptive sizing, you have this kind of buffer space. So between the young generation, because remember, heap is contiguous. And before G1, GC, the young generation and the old generation were right next to each other. So there was a padding. This was an open space, which the old generation could shrink in a way, not shrink, but add to, or it could be reclaimed. It could be claimed by the young generation. So you have young generation, this padding, and then old generation. So that's how adaptive sizing works. So by default, that space could be claimed by either of them, but because of the complexities in the algorithm, when we turned on adaptive sizing, we found out that it doesn't work adaptively. It's always that I think young generation used to reclaim that space, and and it would never give it back, even if the young generation never grew. And there were lots of other issues. So for maybe about 10 bills, we had enabled it by default, but we have turned it off. And I don't even know if the code is still maintained or not, but that's basically it. It's this hollow space between the young generation and the old generation where you could any one of those could either shrink or grow into. Yeah.
Regarding the garbage collector stages, which of the step or stage causes the stop the world pauses percentile?
So so when we talk about generational collectance, the reason I'm saying this because there is Shenandoah. So if we go back to the world before Shenandoah, all the OpenGDK hotspot were generational. So when you talk about young generation, all young generation collection in those garbage collectors are stop the world.
Yeah.
Okay, all of them. Now the difference that is brought about is by the old generation collection. So for throughput, the old generation collection is full stop the world. So when I say full compacting, that means it stopped the world for everything, for marking and sweep and so MSC is the term, mark, sweep, compact. So it's a stop the world for mark, stop the world for sweep, stop the world for compact. Then comes CMS, where it does mostly concurrent mark, as the name implies. So some of the marking phase is concurrently done, some of it is done in stop the world format. So for example, remark, is stop the world, and initial mark is stop the world. So some of them are stop the world. And then the sweep is done independent. So you can sweep just because it's in space. It's like you reclaim this and it goes into this kind of free list. So it's just a pointer to the free list, saying free list says, okay, this space is free, this space is free, so now the next promotion can go into those spaces. So there's a free list in CMS. And in G1, GC, again, the collection, which is the compaction, is the main thing, is stop the world. So G1, GC, the marking phase is similar to CMS, whereas some of it is concurrent and some of it is stop the world, but the collection is always stop the world, and the compaction is stop the world, in partial or fully.
Is it possible to achieve like compaction without the stop the world?
Yeah, I mean, there are lots of algorithms that do that, yes.
Okay, so if you have some questions else, you can ask them on 6th floor. There will be a press conference with speakers. And also, please vote about this presentation and others using Riga Dev Day app.
Okay,
Thanks.
thanks. Thank you.